So now I'm going to go through an example from NetApp. And this is an example that was, this particular example was presented by our data science intern over the summer. And it's talking about the critical case team. So they handle a particular set of cases related to high business impact. So cases that are potentially very costly. And they spend a portion of their time reviewing active cases that have not yet been escalated to see what kind of soft touch interventions may make sense, or doing other kinds of review process, seeing if it may make sense for them to get involved on it. So currently, this is an ongoing part of their work, and they use a common sense or expert rules-based model for doing this to help kind of select which cases they should be actively reviewing. So what we're doing, I'm basically just going to be first evaluating this process and then talking about some approaches to kind of maybe refine or improve components of this. Now, I think of this problem as more of an analogy. For this example, I simplified it a ton. I'm not actually using the real data or some of the constraints of the problem, but think of this as kind of an analogy as I'm going through this. If you're interested in, if you have ideas though, as you see the problem and you have some kind of insights and you're interested in talking with me about it or providing ideas, please ping me or send me an email, and I'm happy to talk about some of the more details of the problem or project in its reality. Let's say, okay, so I'm going to go through this NetApp example initially, and we're going to say here is this data set, and we have, I'm highlighting first this predicted total. So this column represents this common sense model that I was saying. This is the score that the rules-based model produces. So the higher score is essentially something they're saying has a higher risk of becoming an escalation. The way that they produce the score is by the CA-PA, CA-PB, all of those, that's like part A, part B, part C, part D, et cetera, of the model. Each of these are some rule that they currently use, and they have some multiplier that goes on each of these that then gets added up and produce that final predictive total that is the kind of common sense model. So this is the actual, what I did here was just aggregate all of the scores that were produced each day from this model as it exists. So we see that you either got the case number, and then the date represents the day that it got this score for it. So if the case is open for multiple days, you'll get a score each morning that comes out with this model, and then also the customer that's there. For this particular example, I'm just going to filter this down to just the first day that the case showed up on the report. So here you can see this case 20057, et cetera, is open for a while, so it shows up multiple times. For this particular example, I'm just showing the first day. So to do that, I'm just saying let's group it by the case number, and let's filter to just the earliest date for that case number. So we're essentially just getting the first day that it shows up. So you'll see now each individual row is an individual case, and that represents the first day that the case showed up. Now to kind of, the first process in terms of evaluating how this model is doing is we want to maybe connect this to whether these cases actually became escalations or not. The thing is, though, is that data exists in another database. So it's in this SQL Server data, this Microsoft SQL Server database that has information on whether cases actually end up becoming escalations or not. So to connect to that, first I'm setting up this connection to that database. And then I'm going to run the exact same code on, and this is actually running on the database side. And what this code is doing is essentially saying connect that database and pull out any of the list of the case IDs of cases that have become escalations. Okay, so that's what this is running here. And one nice thing about this piece is that, again, this is running on the database side. So say you are working on something where you can't work on that in memory. This code gets translated into SQL. It actually runs on the server side. Also, whether you're connecting to, say, an Oracle database or a Hive database or wherever your data may exist, it's this consistent syntax. So those maybe subtle changes that happen in your SQL code, you don't have to worry about those as much because you're using the same type of syntax. So now that I have extracted that list of case IDs by if it became an escalation or not, I'm taking my original data and I'm just going to add a column that says whether that case at some point became an escalation. So that's what this thing's doing here, is saying, okay, look at the case number. Does it show up on that list of case IDs that became escalations, true or false? And I've just added that column on here. So now we have this column saying, did the case become an escalation down the road at some point? So now, getting to kind of visualizing this example, to kind of see how this current common sense model is doing, I want to look at the distribution of the scores split by those cases that were escalations and those that weren't. So let's say those cases that ended up becoming an escalation, you may expect that the score they had on that model would be centered further to the right where there's higher scores, right? And those cases that didn't end up becoming escalations, if the model's doing a job, you would expect those to be further to the left. So you can kind of see, okay, how well is this model performing by how well is it separating cases that became or did not become escalations based off of this score. So again, if we're expecting to do well, you'd expect the distribution for cases that became an escalation to actually have higher scores. So let's see what that looks like. Here I'm just saying plot a density plot, which is just going to show me the distribution split by if it became an escalation or not. So here in the teal graph shows the distribution of cases that became escalations, and in the pink graph you see the distribution of cases that did not. And you see a slight separation here where the cases that became escalations are centered at slightly higher scores than those that did not. And you may be saying, okay, I want to have a more formal way of evaluating how well this model is doing. And a common way of doing that is robust to differences in the size of the number of observations in each group is to say, okay, what's the probability that a case that truly became escalated had a higher score than a case that did not become escalated? So let's just say we take a selection from both of these distributions, and we're going to ask, okay, what's the probability that the case that actually became an escalation had a higher score? That's what this question is getting at. And the metric for this is called, if you're familiar with this work, this kind of space, this is what the AUC is. And you would expect that if the model is doing a better job, you would have a higher AUC, meaning that there was a higher probability that the case that actually became an escalation got a higher score on your model. That would be a good sign for the model. The baseline would be 0.5, meaning that there was like that there's like an equal chance between of the case having a higher score or lower score, comparing the groups that either became an escalation or didn't. So that's kind of like the baseline where it's not really doing anything to separate these. If you have an AUC of 0.5, these distributions would basically be like, could be like right on top of each other. So in this particular case, for this example here, again, this is kind of an analogy, but for this example, we see an AUC. I'm just going to pass this data into the AUC function, and I get an AUC of 0.76. So in terms of thinking about, we want to beat this current rules-based model, that's kind of our new baseline. Again, more analogy, there's other metrics that would be very important to look at, but for here, think of this as kind of like the new baseline for the AUC. So what you could do then is, as I said, right now, we connected the results of those scores with whether the cases became an escalation or not. So rather than just using the rules-based model to kind of decide what weight each of these inputs get, we can use a method like logistic regression to kind of optimize how important each of these weights are and how much they should contribute to the model. So after doing this, so I build the model using these inputs as my training set, and then the target being whether it became an escalation or not, and I get these new sets of weights here. So now these are the weights for part A, part B, part C, part D, part E, et cetera, and these are kind of new optimized weights for building this model. Something else that is nice is, or that is good is that here you'll notice that some of these inputs were marked as zeros, saying that those inputs essentially didn't do anything to improve the model. So now we also have a more simple model where we say, okay, these inputs are not necessary for this particular problem. So that's also kind of another advantage that can help you with deciding which inputs were useful. And so again, this wasn't, we didn't go and explore a ton of new variables. This was kind of just looking at, okay, how can we optimize something that's already in existence? And let's plot this new model. If we plot this new model in the same style as I did before, where we have one distribution for those cases that became an escalation, and one set for those that did not, this is what that new distribution looks like. I added in the vertical bars represent the median scores for each of the distributions. And if we just compare that to the old set, you can see a better separation with this kind of new optimized version of that model. So again, this is going through kind of like what that process looks like. Let's say you now want to share this. You can use Rmarkdown and Rmarkdown Notebooks to share via HTML or slides or dashboards. So this is just an excerpt from another project I was working on that shows how you can maybe, if you want to share this with a colleague, you can send this, or maybe an executive, you can share these pieces with them using something like this. And here also, I don't think I have it shown here, but you can include the code snippets as well and have like a table of contents and other ways of kind of just making it easy to communicate what you've been working on. This is the picture of what the HTML looks like. If you were to see what does this look like in our Studio IDE, this is the exact same thing, just from the perspective of what I actually wrote out in the IDE. Also, if you want another good way of sharing this is whenever I'm building things, I will try to put it into functions. And you can, if you have a series of functions that are really useful for a project, you can convert these into a package. If it's something that's public and not super specific to your project, maybe you can share those on GitHub and help kind of the community more generally with the new set of things that you created. Or you can build a little package or script and then share that internally or have it communicate with other applications via an API or other tools. Here, I'm just showing, I took that model and put it into a little package that's just here called Brian Examples. And I have this then passed into a calculated field within Tableau. So there's options like that too, where you can take what you've built and kind of help it communicate with other tools outside of just R as well. And this is what Suresh is going to be going through, how to make this communication happen using a TabPy server. Here I used RServe, but he'll be going through a little bit more detail of what this process is like, and the same thing with Tab. The key takeaways I want you to leave with are, one, just the focus when you're, especially if you're getting started in this space or if you're starting to code more on data science problems, that it's important to build code that's readable and not to worry about it being like really terse and concise, but readability is key. And that this building these kind of like logical chains and piece by piece is a good workflow, especially in the context of data science problems, where you kind of have these iterative processes where you're transforming something and then you're passing in a model and then you're having to make a change on some other data set. That building these into kind of like logical changes is a helpful way of going about common data science workflows. If you're interested in using R, looking at the tidyverse packages, using the tidyverse kind of set of packages or packages that are friendly with the tidyverse or that work with a pipe. Especially in R, there's this issue where you have lots of different academic communities that will build their own package that has this kind of different style, different syntax. And why I like using the tidyverse is that it keeps things a lot more coherent and consistent in terms of just like style and what you're doing. So if you are using R, that's a valuable place to look. And just as you're working, making sure that you're documenting your thought process and communicating what you're working on.